So number 5 is asking which of the buffer solutions described above in 3 or 4 has a lower equilibrium concentration of H+. So 2 ways you can look at this. You can just look at the numbers and compare and say, oh, okay, 2.4, that's less than 7.4 because the exponents are the same, so this one must have a lower one. Or you can say the pH is higher, which means we have a lower concentration of H+ in solution. Or again, you can think to yourself, I have more F- here. It's going to bind up more H+, leaving less in solution. So number 4 has a lower H+ concentration because as F- is added, it binds to H+, removing it from solution. And as we increase the amount of F-, we're increasing the amount that is being bound. It's concentration dependent. Number 6 says, suppose a strong acid, like nitric acid, is added to the buffer solution here. So what's going to happen if we add nitric acid in? We know that nitric acid fully dissociates. So in solution, we have a lot of H+ floating around. Complete the chemical reaction that shows what happens. So again, we have our conjugate base, a lot of it, and an acid. Bases are proton acceptors. So this acid is going to donate its proton to F-, and we end up with HF, aqueous, plus NO3-. And it's a strong acid, so it's going to force its proton on this F-. Describe the shifts in equilibrium concentration that occur after we add some of this strong base. So we're going to look at, do they increase, decrease, what happens? So we have F- concentration. What happens to the equilibrium? Well, as we add more acid, we're going to decrease the amount of F- in solution because it's becoming bound to the H+ that are added. HF on the other side of the equilibrium will increase. Again, because F- is binding to H+ to make HF. So we're going to increase the amount of HF we have. H+ in solution will remain the same because as HNO3, as nitric acid is added, it will bind to the F-. But the original amount of H+ that was in solution will remain the same. It's just the extra that gets added will bind to the F-. And so this way we're keeping the pH the same. So the excess H+ is binding, but initial amount remains. Typically, a buffer will hold the pH fairly constant until a certain point at which time the pH will suddenly drastically change. That's what happens in buffers. In the case of adding nitric acid to the buffer, what chemical event will result in the sudden drop of pH? Well, as the buffer moves along, as the equilibrium changes or shifts with this additional acid being added in, the F- is decreasing. And so it will decrease to a point where there is no more. And when there's no more F- in solution, then the amount of H+ will drastically increase. So the F- is all used up. F- is all used up, so extra nitric acid added starts contributing H+'s. Starts contributing H+ to solution and therefore increasing the acidity or decreasing pH.